This is one of many videos where we're focused on exam style questions, this time on carbon-carbon bond formation. So do the questions and allow me to explain. So in our first exam style question, we are going to look at writing the equation for generating the electrophile in the following reactions. So it's asking you to write that equation, and it's giving you two different reactions here. And we'll start with the one on the top. Now, hopefully you should notice, let's make ourselves some space. Hopefully you should notice that there is a carbon-carbon bond here and a carbon-carbon bond here, and it's all connected. Okay, so if that is all connected and it's a carbon-carbon bond and there's nothing else in there, then it's most likely to be Friedel-Crafts acylation, because we're bonding making a carbon-carbon bond between benzene and a hydrocarbon essentially. Okay, so let's try and write the equation for the generation of the electrophile. Now, most of the time people will make a mistake, and the following mistake will think, well, that's the bit that's been added, so I'll count 1, 2, 3, 4, 5. Now remember, those two carbons, this one here and this one here, are already part of the benzene, so you don't need to count those. So the number of carbons that we have in this additional part is 3. So we've got 3 different parts. So that means, and if we write it in, we can write it in skeletal formula if you want here, we can say, well, if we have 3, there's our 3, and we know with Friedel-Crafts alkylation we need to use aluminium chloride. Okay, now we need a haloalkane to do that, and we know we are bonding in 2 different places. So we'll need a haloalkane that end and a halogen that end and a halogen that end. So let's put a halogen either end. Now remember, I've got 3 carbons and there's 3 carbons there. Okay, and if you want, you can do this in pencil and you can just rub out this bond. So for example, if I rub out this end of this bond here, and I'll put it back in a minute, you can see there's one part and there's the other part, and you can see the 3 carbons that are there. I'm just going to put those back in. Okay, there we go, back in. So 3 carbons. So we've got our 3 carbons. We add our aluminium chloride, but this time there are 2 chlorines on each end. Okay, remember each aluminium chloride reacts with one of those chlorines, so therefore we'll need 2 aluminium chlorides, which means we will end up having 2 AlCl4 minus, okay, which will then mean, remember, if I take the chlorine off, I leave it as an electrophile, and there you have your 2 ends, okay, which will then react with that. Now, if we go down the bottom, we're going to do its structural formula instead. So if we look here and we start rubbing out again, let's rub out. There's your bond there, there's your bond there. 1, 2, 3, 4. So 1, 2, 3, 4. So we know it's 4 carbons long. And we know it's got a double bond in it, which means it is acylation. Acylation also uses AlCl3. Okay? But we've got 4 carbons. So let's do 1, 2, 3, 4. Let's put this acyl group on again. Okay? And then in order to react, it's got to have that and that on the end. Just realised I've done this in skeletal again. I'll do the second half in structural formula just to make it a bit more obvious. Okay? So, if we then do the structural formula, and we go CO, CH2, CH2, CO, and put our pluses on there. Okay, and then plus 2 AlCl4, minus. Okay, so what we have here is generation of electrophiles from creating some quite difficult questions with ringed systems where you can often just make mistakes and go 1, 2, 3, 4, 5, 6. Oh, it's 6 carbons long. No, it's not, because those carbons are originally in the benzene. Okay, so hence 3 carbons on that one, Friedel-Crafts alkylation, 4 carbons on that one, Friedel-Crafts acylation, and you've got it in different types of formula. A very, very difficult question, which a lot of people struggle on, but it's worth having a go. Now, we followed up with another question, which is based upon doing the products instead of predicting the electrophile. Now, let's just make some space, okay, and let's look at the structure of these products. And again, do this before I do have a go. Okay, so if we're looking at this one, first of all, we need to recognize what reaction is. We think it's got AlCl3 in it. It's got an acyl chloride, sorry, on this side here. Okay, acyl chloride, AlCl3. We think it's acylation, or well, Friedel-Crafts acylation. Now this is more complicated, and we deliberately gone more complicated. Remember, we're pushing you up to A star kind of level. So if we put this benzene in, and then we look at this and we go, right, okay, we know the chlorines are going to leave, so these 2 chlorines are going to leave, and then that's going to leave the electrophile on here. So this means it's going to be 1, 2, 3, 4 carbons long. So 1, 2, 3, 1, 2, 3, 4 carbons long. Okay, these will go on position, you see it's on 1 and 4. Okay, and then we haven't done our methyl, so that's on 2 and 3. And I recommend that if you're doing this, okay, number it all, and then it's much, much easier to do. Okay, so that is your product. And again, they're only going to get you to ever bond it in 1 or 2 places, and most likely this reaction is not going to be with acylation. It's probably going to be down here, because there have been examples of this before. Now again, made this a little bit more complicated. It's quite a difficult question, I recognise. Is here is a structure in structural formula, and this is very difficult because we need to understand the structural formula first. So we know that if this is acylation or alkylation, you will join onto the benzene when there is a chlorine in the molecule. So here's the 2 chlorines up here, here's the chlorine here and here. So I'm going to join on this carbon here and this carbon here. So I need to know how many carbons are between those 2, or how many include those 2 and are between them. So that would be, for example, on the part that joins, this will be 1, and that will be 2, 3. That's a branch, so I'm not going to include it. 4, so this is 4 carbons. That means I can then, okay, so that means I can draw 4 carbons just like I have above. Okay, so drawn the 4 carbons. That means that one is done, that one is done, that one is done, and that one is done. Okay, I know I've joined on where the chlorines are. That means on position number 1, I have a CH3. So let's imagine this is position 1, 2, 3, and 4. So on position number 1, I've got a methyl coming off. So let's draw a methyl there. 1, 2, 3. On position number 3, I've got a methyl as well. Let's draw a methyl. Good, right. Now let's count how many carbons we've got. 1, 2, 3, 4, 5, 6. Let's just count they match. 1, 2, 3, 4, 5, 6. Great. Okay, so little checks, which means I can do my product. And again, if you ever get asked things like this, they're not going to expect you to join it all the way around the ring. They just expect it in positions next to each other. And it has been in exams before, but this is really the top of the tree when it comes to the difficulty of questions. So if you can do it, well done. We're now going to do the first of 2 synthesis questions. So one is 2-step and the next one is 4. So we're moving from what you would normally get in the exam up into something quite challenging. Okay, so if we do this in structural, and we'll do the next one in skeletal, and we just go CH3Cl, which is our chloromethane, going to our CH3 3COOH. Okay, so in any synthesis, it will normally be drawn out for you, normally be done for you either in structural formula or skeletal formula, and you just have to connect the dots essentially and just go, how can I get from here to here? Now sometimes it's useful working backwards, and the longer the synthesis is, the better it is to work backwards, but sometimes you can see it going forward. So let's do this one backwards though, and then just go, right, okay, what can we make? What can we make into this? So what can this be made from? So another bit of that helps is that this has 2 carbons in and this only has 1. So there must be a carbon chain length and there must be carbon-carbon bond formation. So hopefully you're looking back and going, right, okay, I think I can make a nitrile into that. Now, can I make a nitrile from that? Well, actually I can. So I've got 2 steps. Now, if I then get rid of my arrows, so I can do this in the forward direction. Okay, so in the forward direction, how can I go from here to here? Well, I can do that with sodium cyanide in ethanol. Okay, how can I go from here to here? Well, I can do that with H plus aqueous, which will also be HCl aqueous, which can also be H plus / or slash H2O. Okay, so essentially 2 steps to go from here to here. And this is very normally accompanied by a yield question or something like that and made into an LOR question. But if you want to go through some examples of that, that will be within the synthesis video where you can try that out. Our last question is going to be a 4-step synthesis. And a 4-step synthesis is more than you'll get in the exam, but it's good to challenge yourself. And this uses quite a lot of skills. So let's have a go. So first of all, you're starting off with chloroethane. So there's your chloroethane. That chloroethane is going to turn into 2-hydroxypropanoic acid. So propanoic, 3 carbons long. And then there's your propanoic acid. That means at position number 1, then 2. Okay, and there's your OH. So we then have a look at the whole thing and we work retrosynthetically again. But we look at it and just connect dots together. So first of all, the thing I'd hope you notice is that it's gone up in terms of number of carbons. So there is 2 carbons here, there is 3 here. As well as it going up in carbons, you've got to think of how does it do that? Now it does that, and the big clue is that there is a hydroxy there. If you ever see a hydroxy there, okay, that means that this may have come from a hydroxynitrile, because a hydroxynitrile would add on the extra carbon. Okay, and a hydroxynitrile can come from an aldehyde, okay, but it can also come from a ketone. Now, the thing about the ketone is that you form this kind of product where you've got the OH and the CN, then we usually have an R group either side like this. So have it like that. So if you look at that, you can't really see that. You'd have to have, this would be the R group, this would be the R group, and then you'd have to have the CN coming down. Now, if you have an aldehyde, it looks like this. So it would have your OH there, okay, it would have an H, and it would have a CN like this. Okay, so if that's the case, that means the OH is on the carbon that's next to the CN. So if I know, for example, if I think I can get my carboxylic acid here from a CN, so let's draw it out. Well, there you go, I can get carboxylic acid from there, you saw from the previous example. Okay, this fits that because there's a H coming down here, an OH. It doesn't fit the ketone. Okay, so therefore this will then work back to an aldehyde. Okay, now I need to bridge the gap between here and here. What can I make an aldehyde from? Well, I can only make an aldehyde from a primary alcohol, and I can make a primary alcohol from a chloro. So we've done most of the work, which is great. Okay, but now we need to make it go in a forward direction. So if we get rid of all of these and just put it in a forward direction. Okay, so here we go. Let's do some contrast and do it in pink. Okay, so there we go. How do you go from there to there? Sodium hydroxide aqueous. Okay. Now, how do we go from here to here? Now that is H plus Cr2O7 2 minus. Okay, and really important, that's not finished off. I want to make the aldehyde, so therefore it is distill. Okay, then take the aldehyde, take it to the hydroxynitrile. That is sodium cyanide and H plus aqueous. Okay, so we're doing really well here, and then we go from here, there to the carboxylic acid, that's H plus slash H2O. Okay, and we have a 1, 2, 3, 4 step synthesis. Quite difficult, but you can do it if you try, and I would recommend that you try as many of these as possible because they're actually really quite enjoyable. My class, or my classes over many years, always find them difficult at first, but if you keep doing, you find they're really, really good, and it's really, really good for your revision. So doing synthesis is great, and it's really enjoyable. Well, I enjoy it anyway.